Hello friends, today's topic for discussion is the energetics, kinetics and mechanism of organic reactions. This is actually a continuation of our earlier discussion on thermodynamics of organic reactions. Now, energy, as you know, that all chemical reactions involve energy. Energy is used to break bonds in the reactants. Energy is released when new bonds are formed in the products. So the energy absorbed or the energy released during a chemical reaction, that is known as delta H. That is the enthalpy change or the heat of reaction. Okay, this is enthalpy change or heat of reaction. This is the energy absorbed or the energy released during the process of a chemical reaction. Now, with this delta H, we have seen it can be either positive or it can be negative, positive or negative. That is, in the case of positive delta H, energy is absorbed and the reaction is known as endothermic reaction. So when delta H it is negative, energy is released and the reaction is exothermic reaction. Okay, now bond breaking. Okay, in a chemical reaction, the bonds are broken and the bonds are formed here. Now, bond breaking, it is an endothermic reaction because energy is absorbed. Energy is needed for breaking the bonds. Okay, now bond making, it is an exothermic reaction. That is bond breaking, bond making. Bond breaking means energy is needed. Therefore, it is an endothermic reaction. And bond making, during the process of making the bonds, energy is released. Therefore, it's a exothermic reaction. Okay, now the overall energy change, enthalpy change, delta H overall, we know, it is the sum of the delta H of all bonds broken and delta H of all bonds formed here. Okay, this is the formula by which we calculate the overall enthalpy change. That is in a reaction in which several bonds are broken and several bonds are formed. Okay, now the total enthalpy change, that is known as the delta H overall. That is the sum of delta H of all bonds broken and all bonds formed here. Okay, now this will be the first part of this equation. It is plus value, it will be plus. It is a positive value here. Okay, because the energy is needed for breaking bonds here. Now here this will be a negative value because energy is released during the process of bond formation here. Okay, now all exothermic reactions, the products will be of lower energy. That is, exothermic reaction means the products will be lower energy than the reactants. That is why it will result in the release of heat or release of energy here. That is in the case of an exothermic reaction. And in the case of an endothermic reaction, it will be the converse. That is, the products are higher in energy. Exothermic reaction, we have seen the products are lower in energy than the reactants. But in the case of an endothermic reaction, the products are higher in energy than the reactants. Therefore, continuous supply of energy is needed for the reaction to proceed further. Okay, now we will be considering certain important aspects of thermodynamics here. That is the energy diagrams. Energy diagram means, now you see this energy diagram, it's a very important piece of information it can give here. Okay, it will show you the energy diagrams. That is, it can give you, it will show you that is the energy changes that take place during a chemical reaction. When the reactants are converted into products, the various energy changes. Okay, the energy changes that take place when the reactants are converted into products. The energy diagrams will tell you. Okay, now energy diagrams, it is useful to indicate how readily a reaction proceeds. That is a useful, very useful information. Okay, the readiness, that is how readily a reaction proceeds. It can tell you then how many steps are involved. Okay, and how many, what will be the relative energies okay, of the reactants or of the products or of the intermediates, and so many information the energy diagrams can give you. Now let us see how this, what is meant by this energy diagram here. Now we will be just considering a hypothetical equation, that is a chemical reaction involving two species here. Okay, now the first species, we can say a reaction involving AB. It is a molecule, then it is reacting with an anion here, C minus, so this will be giving you plus BC. So this is the equation. That is, here this bond, AB bond is broken and a new bond, BC bond is formed here. That is the thing. Now here, that is the electron displacement, we can show it in this fashion. That is the electrons in the bond, AB bond, it is getting shifted and concentrated on A. That is why we are getting A minus. Okay, so negatively charged here. That is, in this hypothetical reaction, now let us presume, or rather, if the reaction takes place in a single step, that is, there are no several steps involved here. Usually the reactions do not take place in a single step, but so many steps will be involved here. It's a multi-step. Most of the organic reactions are multi-step mechanism. It will be following the multi-step mechanism. It will be proceeding in different stages or different steps. Okay, now here in this thing, let us presume that this is a single step. Single step reaction means the AB bond, it is broken. At the same time, the BC bond is formed here. If the reaction occurs in a single step, the bond breaking and the bond making, okay, it takes place simultaneously. That is, the bond between A and B is broken as the bond between C and D is formed here. Now, assuming that these products are lower in energy than the reactants, that is, the reaction is an exothermic reaction. Okay, that is, the products are lower in energy than the reactants. Correct. Now here the reaction, we can show this coordinate, that is the energy we will be plotting. This is the y coordinate here, y axis here. Here we will be plotting. This is the energy and this is known as a reaction coordinate. Here, x-axis here. Okay, x-axis, we will be plotting the progress of the reaction here. Correct. This is known as a reaction coordinate. Now, this is our AB. That is our reactants here. AB plus C. This is the energy level of the reactants here. When these reactants, they approach each other, what will happen here? I will just clear off this area. Okay, now these unit species approach each other. There will be electron cloud repulsions here. Therefore, the energy, it will be shooting up. Okay, now this energy of the reactants we can see here. See, so this, it will be going through a hill. This is known as energy hill. Then it will come down like this. So this is the product stage here. This is the energy of the products here. Correct? So this is the energy of the reactants. Okay, now this is the our heat of reaction, that is the enthalpy change here. Delta H of the reaction here. Correct? This is delta H. Now this is the energy of the reactants and this is the energy of the products here. So this part, this point, this is the energy hill, or this is the transition state here. Okay, of the reaction, transition state. Or this is also known as the energy barrier here. Correct? So, and this one, and here we get the products here. That is, which are the products here? A minus plus BC. Correct? So this energy difference. That is the energy difference between the transition state and energy of the reactants here. So this is the energy of activation, EA. So I will explain to you all these terms here. Okay, now what will happen if the as static materials here, A, B and C. Okay, now when they approach one another, their electron clouds repel here. Then it will cause an increase in the energy. Okay, until a maximum value is reached here. Correct. So this unstable energy maximum, that is known as a transition state. So transition state is an unstable energy maximum. Okay, first point you have to understand, it is an unstable energy maximum. It is called transition state here. Now in the transition state, what will happen? In either, the AB bond here, this AB bond, it can be partially broken, and the BC bond, it can be partially formed. These are the two options here. Okay, at the transition state here. Now there is a confusion. What is to be done? Either, the products BC is to be formed, or the reaction should proceed in the reverse direction. These are the two options or possibilities here at the transition state. The reaction can either proceed in the forward direction or it can proceed in the backward direction. That is, the partially broken AB bond, it can reunite to go back to the reactants AB, or the partially formed BC bond, it can form a fully developed bond, BC bond, and form the products here. These are the two options here. Okay, now this transition state here. Okay, now let us see what is this transition state. The transition state means, okay, this is the least stable configuration. Transition state is the least stable configuration through which the starting materials pass during their conversion into products. That is, the starting materials, they get converted into products. So therefore, this is the least stable configuration through which the starting materials pass during the process of their conversion into the products here. So it is generally referred to activated complex. There is another word used here, activated complex. Okay, so this is also another word used for the transition state here. That is, there is merely a highly unstable state. Okay, so that is passed through in a dynamic process here. It is not a discrete molecular species, or it is not an intermediate that can be detected, or it can be isolated. Nothing can be done here. It's a most unstable state here. Now, the transition states here, they are usually represented in this fashion. That is, AB bond here, it is partially broken, and BC bond, it is partially formed here. Therefore, this is the way the transition states are represented here. That we will be using the dashed lines, okay, dashes. And here there will be a partial negative charge and there will be a partial positive charge. And this is a double dagger superscript. Okay, a superscript double dagger. This is the way transition states are usually represented. It's a rough way or representation of a transition state. That means it will be somewhere, okay, we can say between the starting materials and the products here. Okay, the partially broken bones and partially formed bones and all this kind of a thing here. Okay, now here A will acquire a partial negative charge and C will acquire a partial positive charge here. This is the transition state here. Okay, now you see this A will gain a negative charge. Okay, partial negative charge. C will lose a charge here. That is in the course of the reaction. Correct. Therefore, this is the transition state here. Now, in the transition state, we have seen what are the possibilities here. The possibilities are either AB bond, it can reform to generate the static materials, or the BC bond, it can form to generate the products here. Correct. Then, as the bond, okay, it forms between B and C, that is a new bond. That after breaking of the AB bond, the new bond B and C forms here. Okay, the bond forms between B and C here, the energy decreases, okay, until some stable, okay, energy minimum of the product is reached here. So this is the stable minimum area of the products, it is reached here. That is when the bone formation takes place here. Bone formation between B and C take place means the energy will decrease here until some stable energy minimum it is reached here. Okay. Now the energy difference between the reactants and the products here. Okay, that is delta H. So this delta H, it will depend, it will indicate the relative positions of, it will determine the relative position of the reactants and the products here. Okay, this is the energy difference. Now that we have indicated here, delta H here. Okay, this delta H, it is the difference between, energy difference between the reactants and the products here. Okay, now the products are at a lower energy. Okay, products are at a lower energy than the reactants. Therefore, the reaction is exothermic. Okay, and energy is released here. Reaction is an exothermic reaction because the products are of a lower energy compared to the reactants here. Okay, the products are at a lower energy compared to the reactants. Therefore, it is an exothermic reaction. Now, important point, the energy difference between the transition state and the starting materials. Okay, so it is called the energy of activation, EA. This is the important thing here because this will indicate the rate of the reaction, energy of activation. So what is the significance of this energy of activation, EA? Activation energy, that is the energy between the unstable transition state here and the static materials, energy of the static materials. It is called the energy of activation, EA. Correct. Now, what is the significance of EA here? EA means that is the minimum energy needed to overcome the barrier. This is the energy barrier, we can say. And any reaction to proceed, they should overcome this energy barrier. That is the energy hill. So the energy barrier means it is the minimum amount of energy needed to break the bonds here. Okay, then only the reaction will proceed. The bonds are to be broken first. Correct. So this is the energy barrier. So then this must be overcome for the reaction to proceed. Correct. So it is the minimum energy it is needed for the static materials to get over the energy barrier. That is, the bonds are to be broken and the energy barrier is to be overcome. Therefore, some minimum energy is needed. That minimum energy, it is known as energy of activation here. Correct. Now, the size of the EA, that is the quantum of the energy of activation. It will, it will indicate the rate of the reaction. Okay, so the size of the EA, it will tell us about the rate of the reaction here. Now, the larger the EA, what does it indicate? That is the activation energy very high. That means more and more energy is to be supplied for breaking the bonds. So when the more and more energy is to be supplied, the reaction will automatically slow down. It will be a slow reaction. Okay, that is the more the value of EA, that is the larger the value of EA, the greater the amount of energy needed to break the bonds here. Correct? Therefore, the slower will be the reaction. A slow reaction, it will have a large EA. If you put it in the other way, if the energy of activation is very high, the reaction will be slow. And if the energy of activation is low, the reaction will be fast. Okay, that is how we have to see the rate of the reaction here. That is the energy of activation, EA, the greater, that is the larger the EA, the energy of activation is very high, it means the greater amount of energy is needed for breaking the bonds here. Then only the reaction will proceed. Therefore, the reaction will automatically, it will be a slow reaction. That is a slow reaction, it will have a large value of EA. A fast reaction, it will have a low value of EA. Okay, now we can see like this, we can see so many curves we can draw, so many types of reactions we can show here. depending upon the conditions. It can be endothermic, it can be exothermic, and all these kind of things here. So now this is the case where it's an exothermic reaction. The products are at a lower energy here, correct? Now the products are at a higher energy. How will you show it? It is exactly same way we'll have to show here. That is endothermic reactions. In endothermic reaction we can show it in this fashion. Same thing here. This is the energy, and this is the reaction coordinate. Okay, now here the reaction will proceed here. The reactants are here. So like this it will go and it will end up somewhere here. Correct. That means this is our delta H here. This is the energy of the reactants here. This will go. So this is delta H. And this is our energy of activation. Okay, somewhere like this we can just draw. Roughly, I am just showing you a rough idea I am just giving you. So this is our energy of activation here. So in this reaction, we can see, the energy of activation, it is a large EA, therefore it is a slow reaction here. So here delta H, it will be, delta H is positive. It's an endothermic reaction. Correct? Now the products are at a higher energy here. Products are at a higher energy. Delta H is positive. Endothermic reaction. Like this, we can show different situations. When the, what you call, this is a high energy of activation. Now suppose a low energy of activation means, again, we can see the curve, the nature of the curve, it will be changing here. That is the energy of activation, it will be low. So we can show it will be more or less of a flat kind of a thing here. Low energy we can show here like this, So this will be the reactants. Here it will be the reactants here. So this is the thing. So here the delta, so EA it is a low value here. Low value means fast reaction. EA. So this is delta H here. So this delta H here, low energy of activation. So low energy of activation means, so the fast reaction here. Okay. Low energy of activation is fast reaction. We have seen that larger the EA, the greater the amount of energy needed to break the bonds. Therefore, the slower the reaction rate. A slow reaction, it will have a large EA, and a fast reaction will have a low EA. You know that. Now here in this case, the EA is low. That is, it's not, compared to the other case, the EA is low means the reaction is a fast one. Here, delta H, that is the products are at a higher energy. Products are at a higher energy. It means it is a endothermic reaction here. Okay, this will be delta H is positive here. Delta H positive means it is an endothermic reaction here. Okay, now similarly we can draw, these energy diagrams in different situations here. Correct. Now I will just introduce you to an interesting concept here. Now we have seen it's a single step mechanism. Beginning we have seen single step mechanism, that is the reaction is proceeding in a single step, that is bond breaking and bond making take place at the same time. Simultaneously it is happening here. Now if this reaction takes place in a multi-step, that is more than one step, two-step mechanism or a multi-step mechanism. Okay, in a multi-step reaction there could be a reaction intermediate here. Correct. There could be a reaction intermediate. two-step reaction, we can consider many reactions involved, breaking of several bonds and formation of several bonds. You know that. Okay, so in a multi-step reaction, there could be a reaction intermediate. Okay, there will be. So, the same way, we can just consider a reaction of this nature here, AB, that is a, AB uh, plus C minus. So, this is the reaction we have been discussing here. So, this will give you A minus plus BC. Okay, now assume that this reaction is proceeding by a stepwise mechanism. Okay, that is a path, stepwise pathway we call it. Stepwise, different steps, pathway. That is a mechanism here. Okay, this is our first assumption. So we presume it is not proceeding in a single step here. Okay, the reaction proceeds by a stepwise pathway. In that case, the bond breaking takes place first. Okay, then the bond making takes place. That is what is meant by pathway, stepwise pathway. Stepwise mechanism means one step takes place first, then the other step here. That is the AB bond, it is broken first. Bond is broken before BC bond is formed here. Okay, bond breaking occurs before bond making. That is what is meant by stepwise pathway here. Okay, so this is one assumption we are making, and the other assumption is it's an exothermic reaction here. Correct. Now, how the reaction will proceed? You see, one stepwise mechanism, it will involve the heterolytic cleavage. Heterolytic cleavage of the bond here. AB bond, it breaks heterolytically. Heterolytically means the electrons forming the bond, they are unequally divided, and therefore it will result in the formation of ions. Okay, heterolytic cleavage means, it is an ionic cleavage. It will be resulting in the formation of ions here. Correct. So this is the first step here. In one step, that is heterolytic cleavage, that is a one possible mechanism we can say. One possible mechanism is the ionic cleavage, that is heterolytic cleavage of the AB bond here forming two ions. Correct. Now, let us see. Let us write down the mechanism here. Now, this A minus is formed here. This and there is a B plus. Okay, the B plus will be the reaction intermediate here. Okay, now this B plus, it will combine with, in the second step, the C minus anion to form the products here. That is how step 1 and step 2, I will just write it here. So now this is not needed. So what will be the heterolytic cleavage? Let us see how it will be taking place here. Okay, two-step mechanism here we are presuming exothermic reaction. Therefore, it will be, say, step 1 will be, we have seen this is a heterolytic cleavage. Okay, of the heterolytic cleavage of the AB bond here. Therefore, this will be like this. AB bond, heterolytic cleavage means this is electron displacement, we can show here like this. So we will be getting A minus B plus. Correct. This is the ions are formed here in the heterolytic cleavage here. Now in the step 2, what will happen? This is our step, this is step 1, and this step 2, B plus, that is a cation formed here, C minus. So this will form the new bond here. Correct. So the bond AB will be broken. Breaking of one bond, it takes place first. That is, both the things do not take place. That is, bond breaking and bond formation do not take place simultaneously here. Okay, one is before the other one. That is, bond breaking take place before bond making here. Correct. So B, it is a intermediate here. Okay, this B, it is formed in step 1. The cation B, it is formed in step 1 and it is consumed in step 2 here. So when we draw the energy diagram, each step here, okay, each step will have its own energy barrier. That is a transition state here. There will be two transition state. Transition state for step 1 and transition state for step 2. That is two energy barriers. We can draw two diagrams here. And if you want, we can draw a combined diagram also here. Here, step 1. What is the step 1? it is here endothermic reaction. Delta H is positive here because energy is needed for breaking the bond. Delta H positive. Correct. Step 1, it is an endothermic reaction because energy is needed for the cleavage of the AB bond here. Correct. Therefore, the products are at a higher energy than the reactants here because it is an endothermic reaction. Step 1, energy is needed for breaking the AB bond here. Therefore, it is an endothermic reaction, and the delta H here, that is enthalpy change, it will be positive. So product will be at a higher energy than the reactants here. Okay. Now the transition state AB, that bond will be partially broken here. That is the first thing. That is the AB bond, it will be partially broken in the step 1. Okay. Now in the step 2 will be exothermic. First one is endothermic because of the bond cleavage is involved. Step 2 is exothermic because a new bond BC is formed. Therefore, here delta H is negative here. Correct. This is an exothermic reaction here. Step 2 is exothermic. Correct. Energy is released here. BC bond making. The bond delta H, it will be negative. Correct. Delta H is negative. The products will be at a lower energy. In the second step, the products will be at a lower energy, and in the first step, the products will be at a higher energy compared to the reactants here. Okay. Now, because in step 1 is endothermic, energy is needed to cleave the AB bond here. Delta H is positive. Products are at a higher energy. And in the transition state, the AB bond will be partially broken. Now, in the step 2, the BC bond making. Okay, step 2 involves the BC bond making here. That's in the bond making, energy is released here. Okay, now delta H, it will be negative. The products will be at a lower energy compared to the reactants here in step 2. And the transition state will be BC. That is the bond, it is partially formed here. This will be bond breaking and bond making here. Step 1, bond breaking. So, in the transition state, bonds are partially broken. AB bond is partially broken, and in the step 2 transition state, the BC bond, it is partially formed here. Okay. Now, the energy barrier will be, I will just draw these diagrams and show you after these explanations are over here. Okay. Now, the energy barrier for step 1, it will be higher. Energy barrier for the step 1 will be higher because energy is needed for breaking the bonds here. Because the bond cleavage in step 1, it is a difficult process, more difficult compared to bond formation in step 2 here. Okay, therefore the energy barrier, the transition state in step 1, it is higher than the energy barrier for step 2. Okay, this is because the bond cleavage, the step 1 involves the bond cleavage, it is a more difficult process compared to the bond formation in step 2 here. Therefore, a higher energy transition state for step 1. What will happen? More energy is needed here. That is, it will become a slower step of the reaction here. That is, the higher EA means slower reaction. You know that. Okay, fast reactions, lower EA. Slow reactions, higher EA. Correct. Now here, step 1 transition state, higher energy transition state for step 1. So, it will make it a slower step of the mechanism here. So, in the multi-step reaction, in a multi-step mechanism, reaction mechanism, we can say the step with the highest energy transition state, it is called rate determining step here. Okay, this is a very important terminology, that is rate determining step. You will be coming across this term every here and there now in reaction mechanisms. Rate determining step. Simply you understand rate determining step, it is the slowest step in the reaction mechanism. Okay, step 1 is the rate determining step here because it is the slowest rate in the reaction mechanism here. Correct? So there's a multi-step mechanism. That is, several bonds are broken, several bonds are formed. Multi-step. Reaction proceeds in several steps here. In that case, the step with the highest energy transition state, okay, that it is called a rate determining step. So that will be the slowest step in the reaction here. Therefore, here step 1, it is a rate determining step because it is the slowest step in the reaction mechanism. Okay, slowest step. That is what you have to understand here. So now, in the the first step, how it will be. Let us see the first step. So here, all these things I am going to change. Because the two-step mechanism, I will just show you how these energy differences are relative energy positions, So bone breaking involves energy here. Okay, now this is our reactance AB. Now energy is supplied. So what will happen? This, it will go to the hill here, energy hill. Then the products are at a lower energy here. Correct. This is the energy of the reactants and this is the energy of the products here. Correct. This is our enthalpy change. Here, what are this thing? A minus B plus. Okay, B plus is the reaction intermediate here. Correct. So, now this is our EA. This should be a straight line. Okay, roughly I will be showing you. This is EA1. We can say that energy of activation 1. Okay, now here, this will be the delta H1. That is for step 1. Okay, so this will be the step 1 mechanism here. Step 1, here the AB bond, it is partially broken. So this is our transition stage here. That is, this will be delta minus, that is a, so this will be partial negative charge here and this will be a partial positive charge here, double dagger it is known as here. So this is a step 1 transition state here. Okay, AB bond, it is partially broken here. Now delta H1, it is a positive here. Okay, delta H1, it is positive because it is a endothermic reaction. The energy is needed for breaking the bond here. Okay, endothermic reaction, step 1, endothermic. Step 1 transition state is like this only. Correct. Delta H1 is positive. Step 1 I have written here, delta H1 I can write here. That is positive here because the energy is needed to break the bonds here. Therefore, the energy of the products, it is higher than the energy of the reactants here. We can see from the energy diagram here. Now, in the second step, energy diagram for step 2, how it will look like? So, in step 2 means the products will be at a lower energy level. Correct. So, delta H is negative here. Step 2. The same way we can draw the energy diagrams here. Okay, step 2. This is the energy only in this axis. Okay, this is the energy coordinate, reaction coordinate here. So here, the B plus C, that is our starting material here. B plus intermediate plus anion C minus here. So here this will go like this, then this will come down because the delta H for step 2 it is negative and the products are at a lower energy. So this is the energy of the reactants here. This is EA2, that is energy of activation 2. It has got a smaller value here. So and this will be our delta H2 here. So here we are getting the products BC. So this is the energy difference between the reactants and the products here. Okay, so here this delta H2 here, correct? This is the delta H2. Okay, now delta H for step 2. This is a step 2. Transition state will be, how it will be looking like. So for the step 2 transition state will be, that is BC bond, it is partially formed here. BC bond partially formed. So this will be delta plus delta minus. This is our transition state here for step 2. And this is the step 1. Correct. So this is how we have to show this transition states here. Okay, so step 1 and step 2 here. Here in this case delta H for step 2 it is negative and here it is positive here. Correct, because energy is released upon formation of the BC bond here. So this is delta H. We have seen delta H is positive and here it will be delta H negative. Delta H positive, delta H negative. One is exothermic, other one is endothermic here. Okay, so this is the way we have to draw the energy diagrams here. Correct. Now we can, if you want, we can just combine both the things together and combined energy diagram we can draw. So I think you can attempt it by yourself. Now I will just the overall process here, how it will be, that is a combination of both the steps here, step 1 and step 2. Okay, so the combination with the steps, since the reaction has 2 steps, there are 2 transition states here. That is what you were just telling here. Each will be corresponding to a separate energy barrier here. Okay, the transition states are separated by an energy minimum. Energy minimum, we can see the intermediate. That is the B plus intermediate can be seen at the energy minimum here. Okay, at which the reactive intermediate B plus it will be located here. Now, we have seen the difference between the reactants and the products, the delta H, overall delta H. Okay, here it will be with negative value because the reaction is an exothermic. Correct. Overall reaction, it will be an exothermic reaction. Therefore, the difference between the reactants and the products, delta H overall here, it will have a negative value here. Delta H overall will be negative because it's a presumed to be a exothermic reaction here. Correct, negative value. Okay, now the products will be at a lower energy than the reacting starting materials here. Now we have shown here in step 2, the products are at a lower energy than in the step 1 here. Now EA1 here, that is the energy of activation 1. This is the rate determining step here. Okay, EA1 is higher than energy, energy in step 2 here. Correct. EA1 it is higher than the energy barrier for step 1. Therefore, that is EA1, it is the energy barrier for step 1 and it is higher than the energy barrier for step 2. Correct. Step 1 and step 2 transition state, we are comparing the energy of activation. So energy of activation in step 1 is higher than the energy of activation in step 2 here. Correct. Therefore, now because of bond cleavage, you know that it requires more energy than the bond formation. Bond formation means energy is released here. Therefore, a high transition state for step 1, that is what we were discussing here, makes it a slower step of the mechanism here. So the slower step of the mechanism, it is the rate determining step. Okay, that is a slower step. That is a step 1 is the slower step. So that is the rate determining step in the reaction here. Okay, now let us see. I will just briefly give you an idea about the reaction kinetics here. The kinetics of organic reactions. I will not go very much in detail because that you will be learning in physical chemistry, thermodynamics and kinetics and all will be learning here. So briefly, I will take you to kinetics as we are, in of organic reactions here. Kinetics and organic reactions. It will be very interesting. So kinetics means the study of reaction rates. That is known as kinetics. Study of reaction rates is known as kinetics. That means how fast a particular reaction will proceed. Correct. That is when we consider kinetics here. So energy we have seen that energy of activation. So in the energy diagrams we have seen it is the energy difference between the reactants and the transition state. That is the energy of activation. And we have seen it is the energy barrier. Okay. Now the the energy barrier, it is to be overcome for the reaction to proceed. Okay. That is why it is known as an energy barrier transition state here. For the reactants to be converted into the products, okay, the energy barrier is to be overcome here. The larger the energy barrier, energy of activation, you see the reaction is the slowest here. Slower will be the reaction. That is, fast reactions will have a low EA and a slow reaction will have a larger value of EA here. And apart from this, the reaction rates are influenced by the concentrations of the reactants here. Concentration and temperature. Okay, these are the two other variables here. Concentration and temperature also affect the reaction rate here. Now, the higher the concentration of the starting materials here, okay, the higher the concentration, the faster will be the rate here. So, that means higher concentration, faster rate. That is, reaction will be faster. Okay, the higher the concentration, the faster the rate. That means why? Because increasing the concentrations increases the number of collisions between the molecules. Because the reaction takes place by the molecular collisions. When the molecules collide each other, the reaction will be taking place here. So the higher the concentration, the faster the rate of the reaction here. Because increasing the concentrations increases the number of collisions between the molecules here, which in turn will increase the rate of the reaction here. Okay, so we are concerned with the rate of the reaction in kinetics. Simple thing. Okay, now, the higher the temperature means if we, if we keep heating the reactants here, the higher the temperature, the faster the reaction rate here. Okay. Higher temperature means reaction will be faster. Okay, now this, we have seen in thermodynamics delta G, that is the Gibbs free energy change, delta H, enthalpy change, and equilibrium constant, K, EQ. There are so many things we have seen here, but these things have nothing to do with the reaction rate here. Okay, they do not determine the rate of the reaction because these quantities indicate only the direction of the equilibrium. Correct. And the relative energy of the reactants and the products here. That is the free energy change, delta G, delta H, enthalpy change, and KEQ, the equilibrium constant here. Okay, these are all independent quantities here. It has nothing to do with the rate of the reaction here. They do not determine the rate of a reaction. These quantities, they determine only the direction of the equilibrium, whether the equilibrium proceeds in the forward direction or it proceeds in the reverse direction. These quantities will determine. Okay, these delta G, delta H, K, equilibrium, etc., they will determine only the relative direction of equilibrium and not the rate of the reaction here. Correct. And this will also indicate you the relative energy of the reactants and the products here. So it has nothing to do with our kinetics. Kinetics will be an entirely different concept here. Now I will just show you rate equations here. I will not go into the mathematical derivations and all. Briefly, I will introduce you to these concepts here. Rate equation. What is meant by rate equation here? Rate of a chemical reaction, how it is determined? So, rate of a chemical reaction, it is determined by measuring the decrease, okay, in the concentrations of the reactants over a period of time. That is, when the reaction proceeds there, the concentrations of the reactants, it will decrease over a period of time. So, measure that decrease. Okay, that is, rate of a chemical reaction is determined by measuring the decrease in the concentration of the reactants over a period of time, or the increase in the concentration of the products over a period of time. Either way, that is, the reactants are decreasing, the concentration of the products are increasing here. You measure the rate of decrease, measure decreasing the rate of decrease of the concentration of the reactants, or the increase in the concentration of the products here. That is how it is determined here. Okay, over a period of time here. Now it is usually represented, actually we will be measuring it, change in the concentration of the starting materials. That is what we will be determining it here. Okay, that is change in the concentration of the usually it is expressed as a change in the concentration of the starting materials per unit time, in a second or in a minute or whatever it is there. Okay, that is what is meant by rate of a chemical reaction. Okay, so rate of a chemical reaction, it is determined by measuring the decrease in the concentration of the reactants over a period of time, or the increase in the concentration of the products over a time. It is usually expressed as the change in the concentration of the starting materials per unit time. That is rate equation. A rate law, this is also known as rate law. Okay, so a rate law or rate equation, it is an equation rather that shows the relationship between the rate of a reaction and the concentration of the reactants. Okay, that is the rate of the reaction, how the rate of the reaction is related to the concentration of the reactants. That is the rate law or rate equation. It is an equation that will show the relationship between the rate of a reaction and the concentration of the reactants here. Now it is determined experimentally. Okay, it depends upon the mechanism of the reaction ultimately. Correct. So the rate equation or the rate law, it will depend upon the mechanism of the reaction here. So a rate law, now it has got two important terms here. I will not give you the formula and all this kind of a thing here. I will simply explain what is meant by a rate law and all these things, so that you will how we are going to apply it in our organic reactions. That is more important here. So rate law or rate equation. Okay, it has two important terms here. That is the rate constant K and the concentration of the reactor. Rate law or rate equation. It has got two terms here. That is, rate law has two important components here. What are the important components here? One is the rate constant. Rate constant, usually we represent it by the symbol K here. Okay, then another one is the K concentration of the reactants. These are the two important terms here. Okay, rate law, that is the main important terms. The rate equation, it contains the rate constant K and the concentration of the reactants here. Now all the the concentrations of the reactants will not appear in the rate equation that I will be discussing now with you. That is more important for us in the organic reactions here. Okay, not all reactant concentrations will appear in the rate equation. Correct. So now what is the rate constant here? Rate constant means it is a fundamental characteristic of a reaction. Rate constant, it is a fundamental characteristic of a reaction here. Correct. Now this rate constant K, it will take into account the the dependence of the reaction rate, okay, and on temperature and the energy of activation. Correct. So the rate constant K, it is a fundamental characteristic of any reaction. So it will take into account the dependence, how the reaction rate is dependent upon the temperature and energy of activation. We have seen that EA. We have seen. Okay. Now, if the temperature increases, what will happen? That is heating. Okay. Usually, it will speed up the reaction. We know that. Concentration increases, reaction rate goes up. Temperature increases, the rate of the reaction, it will go up here. So the rate constant and the concentrations here. Now fast reactions, we have seen, have large rate constants. Now let us examine, it will be very interesting, fast reactions, how it is related to the energy of activations. Let us see. Fast reactions, it will have a large rate constant. Large rate constant, fast reaction. Then conversely, slow reactions means it will have a small rate constant. Small rate constant. Therefore, rate constant means it will indicate you the rate of the reaction here. Okay, large rate constant means a fast reaction. Very fast reaction will have very large rate constant. In the same way, slow reactions will have very small rate constant here. Understood? Now how it is related to the energy of activation here? It will be just the other way around here. Okay, now we have seen the larger the EA, fast reactions will have small EA. See, we can just compare here, fast reactions. We have seen that is small value of EA, energy of activation, and slow reactions, very high EA. Correct. Now you compare how it will be. It will be interesting here. Now we can say how this rate constant and activation energy, these are interrelated. There is an inverse relationship here. Inverse relationship. Getting the point? That is, fast reactions will have a large rate constant. Fast reaction will have a small EA. Slow reactions will have a small rate constant. Slow reactions will have a high EA. Therefore, K and EA, that is rate constant K and EA, one increases, the other one will decrease. That is an inversely related EA, we can say that. Okay, we have seen that the larger the EA, the slower the reaction. Therefore, the high EA means it will correspond to small rate constant. Therefore, the inverse relationship, K and Ka, that is the rate constant K and the energy of activation Ka, they are inversely related. Okay. Inverse relationship exists. Now concentration terms in the rate constant. So it will depend upon the reaction mechanism. That is what we are telling. So we have seen one-step mechanism, two-step mechanism, multi-step mechanism, and all this kind of thing. Okay. So it will depend upon, in the rate equation, it is dependent upon the concentration here. Rate constant K, concentration of the reactants, rate equation. Okay, now the concentration, what will be the nature of the concentration? It will depend upon the reaction mechanism. One-step mechanism, okay, and two-step, multi-step mechanism here. So in the one-step mechanism, now let me change this page here. What will be the concentration here? That is the most important point here for us, for understanding the nucleophilic substitution reactions and all in the, which we will be discussing later in other classes. So now the concentration terms, now we can say the one-step mechanism. So one-step mechanism means what? The bond breaking, it will, and bond making, bond breaking and making take place simultaneously. We have seen that is rate of equation, it contains the concentration terms for all the reactants here. In the case of a one-step mechanism, that is, the one-step mechanism means rate equation. It will contain, it will contain the So rate equation will contain concentration terms of all reactants. Concentration terms of all reactants will be there here. Okay, so in the multi-step mechanism, what will happen? See, the rate equation, it will contain concentrations of the reactants involved in the rate determining step here. Correct. Here, concentrations of the reactants in the rate determining step. Okay, this is the difference here. That is a one-step mechanism and a multi-step mechanism here. One-step mechanism, the rate equation, it will contain the concentration terms of all the reactants involved here. So in a multi-step reaction, the rate equation will contain the concentrations of only those reactants involved in the rate determining step. That we have discussed what is a rate determining step and all these things. Okay, so the reaction is faster if the activation energy it is lowered here. Okay, now decreasing EA increases Ka. That we know that the inverse relationship is existing here. So I will just briefly tell you a mechanism. Example. Now a one-step mechanism will be one-step mechanism, say this AB. Okay, now this is reacting with C minus. It will give you, this is a hypothetical equation. I am just following every word here now. We see, in this equation, both reactants appear in the initial state here. Okay, in the transition state, we have seen, so both the reactants are involved here. In the transition state, we have seen that AB bond, it is partially broken, and the BC bond is partially formed here. One-step mechanism, we have seen both reactants appear in the transition state here. Okay, now the both reactants are involved in the one-step mechanism. Therefore, both reactants determine the rate here. Therefore, the rate will be rate, that is equal to rate of the reaction, it will be K, that is the rate constant into the concentrations of AB, then C minus. Okay, this is the thing. Now, here, this type of reaction, they are known as a bimolecular reaction. So, one-step mechanism here, both reactants appear in the transition state here. Both reactants are involved in the one-step mechanism. Therefore, both reactants, the concentrations of both the reactants determine the reaction rate here. So, rate is equal to K, that is the rate constant into concentrations of AB and C minus here. Now, it is a bimolecular reaction. It is known as a bimolecular reaction here. Now, what will be the order of the kinetics here? That is, we will be seeing the sum of the exponents here, of the concentration terms here. Okay, these reactions are bimolecular. Now, what is the order of the kinetics here? That is, order of the kinetics is K. Now, this is AB. That is, the exponent is 1. And C minus exponent is 1 here. Okay, therefore, the order of the kinetics will be 1 plus 1. That is sum of the exponents. That is 2. Therefore, it is a second order reaction or second order rate equation. We call it second order kinetics here. Okay, that is the sum of the exponents of the concentration terms here. So each concentration term exponent, it is 1. KAB means KAB raised to 1. C minus raised to 1. Therefore, 1 plus 1 is 2. Therefore, it will be a second order rate equation. That is, the order of a rate equation, it is a sum of the exponents of the concentration terms in the rate equation. Got the point? That is, what is the order of a rate equation? order of a rate equation. Correct. Order of a rate equation, it is the sum of the exponents of the concentration terms in the rate equation. Correct. Here we have seen two concentration terms are here. In a one-step mechanism, we have two concentration terms here. Therefore, reaction follows a second order kinetics. We call it second order rate equation or second order kinetics. Correct. This is a one-step mechanism here. Okay. Now, so therefore, here the rate depends upon the rate of the reaction. It depends upon the concentrations of both the reactants here. Okay. Now, if you double the concentration, what will happen? Okay. AB, we are doubling it, and the C, we are doubling it. If you double both simultaneously, both AB and C, it will increase the reaction rate fourfold. Okay. Now, if you increase either AB or if you increase either or C, correct, it will double the rate of the reaction here. Okay, because so it will depend upon the exponents here. That is the two concentration terms are the second order kinetics. The rate is depending upon the concentrations of both the reactants. Now doubling the concentrations of either of these reactants, either AB or C. In that case, the rate of the reaction it will be doubled. Rate will be doubled. Now, if you double the concentrations of both the reactants here, doubling the concentrations of both AB and C, it will increase the reaction rate 4 times. Correct. That is the situation in the one-step mechanism here. Now I will briefly tell you a two-step mechanism. What will be the nature of the rate equation here? So a stepwise mechanism we can say. This is a stepwise mechanism. Okay. So these are all things which we will be coming across in subsequent chapters in the organic chemistry here. Okay. So two-step mechanism or a stepwise mechanism, how it will be. So AB. Okay. Now AB reacting with the C minus. What will be the thing? This is the equation. Okay. So the two-step mechanism, there will be a slow step. That is the rate determining step here. Okay. In which AB bond is broken. And a fast step in which the BC bond is formed. There are two steps involved. Here, that is a slow step, two-step mechanism we can say. Two-step mechanism, a slow step. This is the rate determining step. Slow step, AB bond is broken. Okay, slow step, this is the rate determining step. Okay, and there will be a fast step. Two steps are there. Fast step in this BC bond formed. Okay, that is not rate determining step. The first one is the rate determining step here. A slow step, two-step mechanism. A slow step in, that the rate determining step will be there. That in which the AB bond it is broken. And a fast step that in which the BC bond is formed here. Now we have seen in the energetics when we are just discussing AB, this bond will be heterolytically cleaved here. So it will be giving you A minus, then a cation B plus here in the step 1 reaction. So this is the step 1. We have seen that. Now here in step 2, this cation intermediate. So it is consumed. Okay, C minus here. So this C minus, it will take this B plus here. Correct. So this is how the reaction will proceed here. So we will be getting the bond formation. New bond is formed here. Now here, which is the rate determining step here? This is the step 1 is the rate determining step. Therefore, because the bond cleavage is involved, that is a slow step here. Okay, that means in the rate determining step AB, that is the concentration of AB is involved. Only AB is involved in the rate determining step. Therefore, the concentration of AB only determines the rate of the reaction here. Therefore, rate will be rate of the reaction will be the rate constant K into AB, because this is the concentration of the reactant at the rate determining step, slow step of the reaction here. Therefore, here KAB means KAB raised to the power 1 here. Therefore, this is a first order kinetics. And the other one is a bimolecular. This is a unimolecular. First order rate equation. Okay, only one concentration term is involved. Therefore, the kinetics is first order. Stepwise mechanism here. Slow step and a fast step. Slow step is the rate determining step, step 1. And in the step 2, this BC bond is formed here. Therefore, only the rate determining step, the concentration of AB, only AB is involved here. Therefore, the rate determining step, AB determines the rate here. Correct. So, the concentration of the reactants affecting the rate determining step, that will appear in the rate equation. Okay. Now, the rate will depend upon the concentrations of AB only here. Correct. A reaction involving only one reactant here. Okay. Now, it is said to be a unimolecular. Other one we have seen, it is a bimolecular reaction. Now, this is a unimolecular reaction here. Correct. That concentration of the reactants affecting the rate determining step appear in the rate equation here. So, the rate will depend upon the concentration of AB. Okay. So, a reaction involving the concentration, reaction involving only one reactant, that is concentration of only one reactant, it is said to be unimolecular. Okay. So, this is the first order kinetics. Other one is a second order kinetics, and this is the first order kinetics here. First order kinetics. Okay. Now, if you double the concentration here, what will happen? If they double the concentration of AB, it will double the rate of the reaction here. Okay. Now, if we double the concentration of C, it has no effect, because C is not involved in the rate determining step. Only AB is involved. Therefore, doubling the concentration of AB, it will double the rate of the reaction here. C, it has nothing to do. C is not involved here. Therefore, doubling the concentration or even removing the C and substituting with any other anion, it has no effect on the reaction, rate of the reaction here. Okay, that is the difference here in the first order kinetics here. Okay, C is not at all involved in the slow step. We are concerned only in the rate determining step, that is the slow step of the reaction here. Therefore, C is not involved in the rate determining step here. Therefore, that concentration term doesn't appear in the rate of the, reaction here. Correct? Now, so neither is concentration or is identity. Rather, we can say that is whether C is replaced by some other C or some other D, whatever it is there, it doesn't affect the rate of the reaction, because this concentration is not there in the rate determining step. That is the important difference here. Okay, rate equations, it will provide a very important information about the mechanism of a reaction that we will come to know later. Okay, so thank you very much for listening.